Happy Wednesday. Couple of things. The ALEX objectives are going to be due on Wednesday at the start of the midterm exam. So next week, you do not have objectives due on Monday. They are instead only due on Wednesday. This will give whatever we discuss on Monday. You can actually work example problems for that. ALEX has the capacity? Sure. If you sign into ALEX, it says welcome, and then it has a pie with like your current score, either in number of objectives or percentage. On the left side, it usually is like dark blue and says continue my path. At the top left of that, there are 3 lines. Looks like a hamburger. If you click that, it's going to pop open a menu to the right. In there, the word review. If it is not grayed out, it is only grayed out if you have a knowledge check and it wants you to do that first. If you click the review button, it will reopen any previous objective that you have seen. So if you want to practice titrations, limiting reactants, anything for the midterm that's next week, you can get there in that way. There are also lots of other online resources for you that you can check out. So that's when your objectives will be due. Next Wednesday, start of class. Some of those objectives are going to move into the future because I don't think we'll finish covering everything I had dreamed of covering prior on Monday's lecture. So some may move out at the very end, but we'll deal with that on Monday. For SI, so supplemental instruction happens on Tuesday, Thursdays, and Fridays. So on Thursday, she will review chapters 1 through 3. On Friday, she will review chapter 4. Next Tuesday, she's not going to hold a practice exam. It's just going to be more of a structured review with problems on, I don't want to call it difficult topics, but what she is relatively confident will be on the midterm exam. Mahi will send you all of that information via her usual method, announcements, emails, however. Does she send emails or announcements? Both? Announcement? Something? However that gets to you, she's going to send you more information about that because usually we take our mini exam, we pretend chemistry does not exist until Monday at 4:30, but I would definitely recommend taking some time this weekend to study for the midterm. Questions? Super. Oh, is it hot in here to y'all, or is it just me like doing this song and dance? Okay. On Monday, I felt like I had gone for a run. Did we finish this example? I know we did that example. Did we do the cylinders? I'm getting mixed in. You know what? We'll start there since we're getting a number of maybe not. Whoops, wrong section. Ow. Try to make sure I stay in the frame. So, in this question, it says, gases A and B are confined within a cylinder and react to form solid C. As the reaction occurs, the system loses 1,150 joules of heat to the surroundings. The piston moves down as the gases react to form a solid. As the volume of the gas decreases under constant atmospheric pressure, the surroundings do 480 joules of work on the system. What is the change in internal energy? So, as a reminder, we are considering delta E equals Q plus W, where delta E is the change in energy for the system. Q and W are heat and work, and those come out of the problem here. And so the difficulty is deciding, are we gaining or losing work in the system? So the heat is negative 1,150 because the heat is being lost, and work is positive 480, so delta E equals negative 670 kilojoules. Just regular joules. Questions about this calculation or this topic? So the reality is delta E, we've talked about it as the change in energy. And so delta E is something called a state function. State functions are things that they kind of have a couple of characteristics. One, they have capitalized letters for their value. So delta E is a capital E as opposed to the lowercase e. So Q and W are both lowercase, so they are not state functions. A state function is path independent. So, hold up. Let me stand back here so that my video audience can participate in this analogy, otherwise it doesn't work. If we want to know the change in my physical position, if I start here and I go here, I don't know, like 6 feet? But that's path independent. If we're talking about just distance, I'm not going to run around because it's super hot in here, but if I were to get really excited and basically run around the back of the classroom and still end up here, the distance between these 2 points has not changed. I just frankly did a lot more work to get here. So work is path dependent. It matters how much work you did, how hard it was to do that work. But the movement or the change in energy between those two is path independent. So the altitude change is probably a good example between New Orleans and Denver. Basically, that is a static, well, mostly static. New Orleans is sinking, but we'll just assume it's not sinking for this calculation. So the difference between those is always the same, whether you drive from New Orleans to Denver or you get on a plane and fly. So that's the difference here. So state functions, we're going to meet several of them. They will always be annotated with capital letters. I'm aware that I use bubbly font when I write with my hand. If you have a question about whether or not it is actually a state function, like W here, my capital W is just bigger. It's kind of difficult to see. If you have any questions, feel free to reach out. Just raise your hand. So state functions, we're going to see a couple in this different chapter. But delta E is the first. So enthalpy and enthalpy of reaction. So what we're going to start talking about, so we talked about the change in energy for a system. And energy is composed of many, 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 many different things. But we are going to mostly focus on the enthalpy of a reaction in terms of enthalpy. And enthalpy is related to heat. So enthalpy, which is annotated as capital H, is the study of the flow of heat. And so if you were to want to calculate enthalpy, enthalpy can be calculated where E plus pressure times volume. So E being energy, and P is the pressure, and V is the volume. Now, just like energy is very, very difficult to determine at a specific time, so is enthalpy. So energy we can really only calculate using heat and work or some sort of a change, a final minus initial. So it turns out for enthalpy, we can also do the same thing. So delta H is equal to delta E plus P delta V, or delta E plus delta P times V. So basically, it's the change of all of these, but when we think about pressure and volume, you can only change one at a time. In Chapter 10, we will talk about explicitly why that is, but for today, you may take, well, however well you trust me in this case. So you can either change the pressure or you can change the volume in a given system. If you try to change both, one, your calculation doesn't work, and two, the system kind of either definitely expands, meaning blows up, or it crumples and collapses. So we get that delta H is equal to delta E plus P delta V. And so this is how we can calculate the change in enthalpy. So if you had delta E, which you could calculate as Q plus W, or the pressure and the change in volume, we could calculate that. So when we think about these systems, we're often thinking about the pressure or the work that is done with the expansion or contraction of a gas. If you, and this is, I have a mask on so it doesn't work, if I were to have a balloon that I was going to blow up, you have to put in work in order to get the balloon to blow up. As you expel air in, the volume is going to expand, and so you're going to have to put work into that. The work is done by the system, as opposed to the surroundings squashing the balloon back down. So we can calculate work, either we know it out of the problem, or work is related to the negative pressure times the change in volume. This is pressure, and this is the change in volume. So in this case, it's negative for a couple of different reasons, and some of that is part of the equation. And so the reason this is slightly negative is if we know that delta H equals delta E, which is Q plus W, plus P delta V, we now know that work is equal to negative P delta V. So delta H is really just equal to the heat. So when we think about the heat of a system, we are thinking about the change in enthalpy. I did a lot of equation derivations here. I will not be asking you to reproduce this. What I'm going to ask you to do is to plug stuff into this equation and this equation. This is just how it all fits together. So if this just made your brain hurt, you can say, okay, lady, I trust you. I'll just use the numbers. That's okay. I also do want to be clear, all of the equations will be on the equation sheet. Not asking you to memorize any equations, any constants, all of that will be present on an equation sheet for the midterm exam or any other exam that we have. So we can now calculate the work in a system. Do you have a question?
Yeah, on the bottom, is that delta H equals Q or minus Q?
That is an equal sign that I got a little carried away on, so it's just a regular equals where they were not the same size. Any other questions? So let's look at calculating work using our new equation. So fuel is burned in a cylinder equipped with a piston. The initial volume of the cylinder is 0.250 liters. The final volume is 0.980 liters. If the piston expands against a constant pressure of 1.35 atmospheres, how much work in joules is done? So we're going to use this calculation. So we know that the pressure is equal to 1.35 atmospheres. And delta V is V final minus V initial. And so in this case, it tells you explicitly the beginning and the end. So we could just plug those in. So delta V equals 0.980 minus 0.250 liters, and that gives you 0.730 liters. So now we've figured out what goes in our equation. So we know that work is equal to negative 1.35 atmospheres multiplied by 0.730 liters. Ignore all that. What units are they asking for in this calculation? Do liter atmospheres equal joules? No. But it turns out there is a direct unit conversion. So this 1 liter atmosphere equals 101.3 joules is the same type of conversion as like 1 kilometer is equal to 0.6-ish. We'll use some big strong ish on that one, miles. This value can be found in the conversion factors or other important information part of your exam. So in this case, we are going to get negative 0.9855 liter atmosphere. We're going to multiply that by 1 liter atmosphere times 101.3 joules, and that gives us negative 99.8 joules. What questions do we have about this calculation? Do we feel relatively confident that we could reproduce this on a different but similar example? Well, let's find out. So, if you scuba dive, your lungs are under a constant pressure of 1.65 atmospheres. Each breath requires 856.6 joules of work. What volume of air in milliliters is exchanged in one breath? Does anyone like to share what they've gotten for their answer? Yeah, what'd you get?
5,124.
Yeah. You have a few too many sig figs? Well, I'll take it today.
Okay.
So how we got to that answer is we know that work equals negative P delta V. And in this case, we know that the work is equal to 856.6 joules. We know that the pressure is 1.65 atmospheres. And we are looking for change in volume. And so the change in volume, if we rearrange our equation, is negative work divided by pressure. And so we have our negative 856.6 joules divided by 1.65 atmospheres. 1 liter atmosphere is equal to 101.3 joules, and this gives you negative 5.12489 liters. To convert to milliliters, we multiply by 1,000, and that gives you negative 5,125, which you can round to 5,000. 5,130. So, he said positive 5,000. In this case, I'll accept both because it actually asks what is the volume of air in milliliter exchanged. And this problem doesn't tell you in reference whether you are starting with no breath and breathing in or a full breath and breathing out. If it did, you would have to decide whether or not the work was in fact positive or negative in the calculation. It will usually tell you in the problem. Just as an aside, this one gives you some ambiguity, and so you could in fact make some decision. What questions do we have about this calculation? Yeah.
I'm a little curious as to why it's rounded to 5130.
So you can only have 3 significant figures.
Correct. But doesn't the 2 not round up since the next number is a 5 or a 4, not a 5?
Can also change that to a 20. Hopefully it wouldn't turn out that way because I think you are correct, but I think I pre-rounded. This is why significant figures are a pain in the keister. So if you round to 4, which I obviously did, then it rounds to 5130. But if you kept it as 5,124.8, you are correct that that rounds down to 5,120. Hopefully, when I design questions, if they turn out this complicated, I change the numbers. So, hopefully it won't happen. A good question. Any other questions? Any other mathematical errors that we are observing that I'm currently making? Yeah. So you took the 856.6 joules and divided by 101.3, right?
Yeah.
You should still get the same. What did you get instead?
The decimal is 5.1233 instead of 5.48. I might have put in a number wrong though.
No, I think sometimes it just matters how you plug stuff in the calculator. So if he got 5,133, is that what, give or take?
Yeah.
Most of the time, if your answer is close, you will get full credit. Now, that's me as a people. We all know that Alex will be like, I don't know, math is hard. But in this case, I will look at your work, and if you get the right work and you're very close, full credit. If you have the right work and something weird happened, I will write something that says -2 ME with a question mark, which means math error. It means you and your calculator have a fight, so that happens. Other questions? So thinking about the work in a reaction or something else is good, but this is Gen Chem 1, and we really want to start to think about reactions. How do reactions occur or not occur? So we know that any reaction, right, if we have reactants goes to products, it probably occurs. In the purpose of this course, right now, it definitely occurs. So we have A plus B goes to C. And thus far, we haven't talked about whether or not it gives off energy or we put energy in. We've just said A plus B goes to C. It turns out that you either have to put energy in or get energy out. So only, I guess it could be neutral, but it never is. So we have to have some energy. So we're going to start to think about delta H reaction. Instead of thinking of a system, we're going to talk about the change in enthalpy for a reaction. Delta H generally is final minus initial. In terms of a reaction, it is going to be the H of the products minus the enthalpy of the reactants. And so there are a well, in terms of Gen Chem 1, there are 4 different ways we are going to learn to calculate delta H reaction. None of which we will get to today. Today we're just going to talk about delta H reaction. Starting on Monday, we will look at different ways you can do that calculation. So for a reaction, delta H reaction also equals Q. So the same Q we talked about, we're just adding a reaction. So when delta H is positive, the reaction is endothermic, so heat is being absorbed into the system. When the heat is absorbed, the outside of the reaction vessel is cold, because all the heat went into the inside from the outside. When delta H is negative, it's exothermic, and the heat is lost to the surroundings, so it will feel hot on the outside. And so the way we can think about this is when delta H is negative, the heat being lost means that energy is being given off. So in this reaction, we gained energy in the system. When it is endothermic, when delta H is positive, you have to put energy into the reaction to make it go forward. So we can think about the enthalpy of a reaction. Thus far, we have talked about reactions where we have A plus B goes to C. And I can give you values for any of those 3 or multiple. You can tell me how much product we will make, right? Limiting reactant style. We're not going to really talk about those. I'm just giving you some examples. How we're just taking it one teeny tiny step further today. And so we can think about the enthalpy of a reaction. So delta H reaction, we are either going to calculate it using some tools, or it will be provided in the question. Delta H reaction is not like balancing an equation. It's more of a standard value. So what you're going to start to see is a reaction followed by delta H equals a value. It's the same or similar to the coefficients. So enthalpy is an extensive property. Delta H is proportional to the amount of reactant consumed. The same way that the amount of product you get is directly related to the limiting reactant. If your reaction changes based on the amount of reactant consumed or present, we're going to see changes to the amount of enthalpy that is produced or consumed. The enthalpy change for a reaction is equal in magnitude but opposite in sign for the reverse reaction. So let's look at an example to give ourselves some thoughts here. So if we have CH4 gas plus 2O2 gas goes to CO2 gas plus 2H2O liquid, and that equals delta H equals negative 890 kilojoules. If we suddenly doubled all of our coefficients, 2 moles of methane, 4 moles of oxygen, we were to have, ooh, this color's aggressive, 2, 4, 1, 4 moles, delta H is going to be 2 times negative 890 kilojoules, and that would be negative 1780 kilojoules. If by chance we were to say, I wonder how much energy it would take to combine 1 mole of CO2 plus 2 moles of water, so we're going to flip this reaction and get CO2 gas plus 2H2O liquid gives us CH4 gas plus 2O2 gas. Delta H in this case is going to be positive 890 kilojoules. Because instead of gaining this much energy, you have to put this much in. So a positive delta H means you have to put in that much energy. And the other thing that's important is that the states of reactions matter. It costs energy to convert liquid water to gaseous water, or something else, or really anything else. And so the reality is, paying attention to these states will matter when we think about Hess's law and when we look at heats of formation. have this example, which is the same reaction we've been looking at, but it asks how much heat is released with 4.50 grams of methane is burned in a constant pressure system. We're looking at this reaction. You can ignore the red part. This negative 890 kilojoules is for any part of the reaction. So it's negative 890 kilojoules per 1 mole of CH4, or negative 890 kilojoules for 2 moles of O2. Because 2 moles comes directly out of the balanced chemical equation. So delta H reaction is given as a value, X number of kilojoules. Oftentimes we'll ask for things like, what about in kilojoules per mole? So students often like to just draw a slash mark and write mole underneath and frankly hope for the best. If the coefficient is 1, you're good to go. If the coefficient is not 1, you're going to be off ratio-wise. So for every mole of methane, you get 890 kilojoules. So we just really need to figure out how many moles of methane. It will be different in terms of moles of oxygen because oxygen is different in the equation. So to answer this question, we are going to take our negative 890 kilojoules per 1 mole of CH4. We're going to multiply that by 4.50 grams of methane that we will then continue on to convert using the molar mass of 1605 grams in 1 mole. This gives us negative 250 decimal place kilojoules as the amount of, or the enthalpy that is released when 4.5 grams of methane is burned. Questions? Well, then let's do another example. So in all of these, there's a typo on this slide. So the aluminum oxide just has a state of A. It should definitely be aqueous. Clearly I deleted the Q when I typed this out or never got there, I don't know. But A should in fact be aqueous. But the balanced chemical equation is shown. That is not a balanced chemical equation, so we'll just, it's not balanced, but we'll ignore that part. So in this case, we will use the example as written, even though it has apparently 3 million typos in it. So for the first one, we're going to take our 41.2 kilojoules per 3 moles of H2O. We're going to multiply that by the 78.1 grams of water. Divide by the 18.02 grams in 1 mole of H2O, and that gives you 59.5 kilojoules. Questions? Would you like to attempt B on your own? That wasn't really a question. It was more of a let's give it our best go. You can use the wildly unbalanced equation. It should have a 2 in front of the aluminum hydroxide. The delta H is the same. I'll give you the value for both. Whether you use the balanced chemical equation provided. And so in chapter 5, you're going to start just using what you have. It will give you a balanced equation. Much more information will be provided in the question. So in this calculation, if you use the balanced equation that I provided, you would get 36.5 kilojoules. If I had provided the correctly balanced equation, you would get 18.3 kilojoules. Again, it's just missing the 2 in front of the aluminum hydroxide in this case. Questions about enthalpy. We're going to use this as a tool a lot for the rest of the chapter. So we're just kind of dipping our toe in. Excellent. I think, yeah.
So 1 mole over 78.01 grams, that's aluminum hydroxide, right?
Yes, that's the aluminum hydroxide. Excellent. Well, I think it's that time for mini exam 3. Yes. Say that again. Yeah.
So on one, like the body oxidation number,